Hello everyone, welcome to the next video of EC573 Advanced Embedded Logic Design Lab. In this lab, we are focusing on the AXI DMA scatter gathered mode. We discuss about the DMA register as well as we discuss about the format of the buffer descriptor. We also discuss about the block diagram where we are going to compare the DMA in the simple mode and the DMA in the scatter gathered mode. Now let's quickly look at the application code, which will use to configure the DMA in the scatter gathered mode, and we can do the simple toy example where we'll have the one buffer descriptor for MM to S and another buffer descriptor for S to MM for the matrix multiplication operation. So in the application code, as we discussed, we need to first configure the MM to S, S to MM, DMA register. We need to create a buffer descriptor. We need to link the MM to S buffer descriptor with our input of the to be passed to the DMA, or input matrices A and B to be passed to the DMA. And we need to link the buffer descriptor of S to MM to the data output of the IP, that is the matrix multiplication output, so that we can compare with our benchmark output. So in the application code, we will have the DMAs in the simple DMA mode comparison that we have already done in the past, and we need to add the additional code for the DMA in the SG mode. So as usual, for any DMA or any hardware IP, we need to take care of the corresponding IP configuration and initialization. So here we are going to have the IP instance and the configuration pointer, so that we can get the corresponding configuration data into the configuration pointer and initialize the DMA instance with the corresponding configuration data. So after that, we'll have the two separate functions. One function for the setting up the DMA of the setting up the corresponding MM to S channel and the S to MM channel. Okay, so for the DMA, there are various examples are there. Sample examples are there in the which are provided from the Xilinx. So this code is taken from that sample example, but it is modified as per our requirement. So if you want to look at the sample example, please have a look at the this one to get the more details. Okay, so now let's focus on the how to configure the MM to S and S to MM setup. So in the DMA MM to S setup, what are the things we need to do? First, to do the setup, we need to read all the hardware information of the DMA, so that we know what is the base address of the DMA. We know whether the SG mode has been set up. We should know we should know the properties of the DMA. So for all these things, what we have is that we have one already defined structure. So this structure is the is of the type AXI DMA BD ring. Here in this structure, you can see that you can collect all the information about the DMA. For example, what is the base address, whether this is the MM to S or S to MM channel, what is the current state of the DMA, whether there is a alignment mode is unable or not, data width, what is the maximum transfer length, that is the buffer length register, what is the first address of the BD, what is the length of the BD, separation between the BD, what are the status of the BD, whether it's a free, how many are in the free state, how many are in the pre-hardware state, how many are in the hardware, or how many are in the post hardware stage, or whether the cyclic mode is enabled or not. So they have already defined a structure where you can collect all this information. So we can make use of the structure. In the beginning, this structure will be empty, and we will make use of this structure. Another thing we need to do is that this is the optional step, is that we can create a BD buffer descriptor template with the minimum information. For example, in case of the buffer descriptor, you know that the first two field corresponds to the pointer to the next buffer descriptor. So we can initialize those once we know that where the buffer descriptors are going to be stored. So we will have the another array for the buffer descriptor as well to store the to have the template for the buffer descriptor. So if you see this one in the beginning, everything about this structure is initialized to 0 because there is no information. And then to get the DMA specific information, we can use the AXI DMA getRing function. And via using this getRing function, we can get the DMA specific information inside that structure. So after executing this function, you will see that you got the base address of the DMA, which we have instance we have given. We know that this is the MM2S, so this is not a RX channel, it's a TX channel. Then we have already enabled, while configuring the IP, we have already enabled the alignment mode. Data width is 32-bit. And the maximum transfer rate is 2 to the power 26. So you can see that all this information is taken from the DMA. This information is not there because this is the BD specific information and we have not created any BD. So this information is not there. So now next thing is that we need to configure the DMA as per our requirement, and we need to set up some dummy buffer descriptor. Now, in case of the DMA configuration, if you remember, we need to write the current descriptor, then the tail descriptor. We need to use update the control register where we need to enable, disable the interrupt. We can set the cyclic mode. We can start the DMA by using the RS bit. So what we are going to do is that first thing is that we are going to disable the interrupt. So here you can see that I'm going to disable the interrupt. Now to disable the interrupt, again we'll write the appropriate values here 0, and by using the debugging mode and by using the XCST control, you can read the appropriate register inside the DMA. For example, this is the base address, and at the 0th location, you know that the control register of the MM2S. So you can read that register, and you can see that the value is 0001 0002. The 0002 means these 4 bits are 0010. That means the DMA is not has started yet. This is the reserved bit which is set to 1 in this case, and then this one. Then you can see that this is 0000. Then so that means this one. Then another 0000. That is this one. Another 000. Yeah, so total, I might have missed one bit somewhere. Okay, this bit I have missed. So this is how you get this 0. Then you can see that this is 00000001 because by default the LSB bit is 1, and this is all 0 and so on. So this is how you can read you can set the control register inside the DMA. Now we have disabled the DMA. Now one step is we need to do in the control register. We need to set the RS bit to 1. Now before setting the RS bit to 1, what we need to update is that we need to update the current descriptor address. Now the current descriptor address we need to update, and for that we need to create the BD descriptor. We need to define the memory space for the BD descriptor. So what we do in our code, we define some memory in the DDR as a which is used to store the buffer descriptor. So the memory which is from 0x0100 to 0000. So this is the where we are going to store the MM2S buffer descriptor, and the memory which starting from this address 0x0 1000. Here we will store the S to MM buffer descriptor. So we have separated out the buffer descriptor for MM to S and S to MM. So we'll be storing here. So if this is the memory, so this is the address of say 0x01000000, then you can have the first buffer descriptor here, another buffer descriptor here, third buffer descriptor here, and so on. So for every buffer descriptor, you can see you can have the some set of memory, and here it is right now we will assume it is the this much amount of memory that is we are going to store. So by using the this function, which is the AXI DMA BD ring create, we can create the buffer descriptor so that the addresses are updated and the corresponding count is updated in this structure. So we will give the base address, which is this one. We'll give the same in this is the virtual and the physical address, which is same in our case. Minimum alignment, which is the what is the minimum size of the each BD, and the BD count. In our case, it is only one because we are going to use only one BD count. So we will give it, and this structure will be updated. So now you can see that after this, you can see that this structure has been updated with the appropriate values. Here you can see that the values have been updated, and you can see that the total count is 1 out of, and the corresponding BD is in the free state. So this is how the corresponding our internal structure has been updated. So now you can see that we have created the BD, we have updated it information in the TX ring pointer. We have not updated it in the DMA register. Now, before we update it in the DMA register, we need to understand what are these 4 states of the DMA. So you can see that there are 4 states of the DMA. Let's understand what are these 4 states of the DMA. So DMA descriptor, not the DMA, it's a descriptor 4 state. So the descriptor by default, it will be in the free state. Then it will go to the pre-process state. It is still in the pre-process state, means it is you are updating the values of the different fields in the BD, but it is not yet sent to the DMA. It will go into the hardware state. That means you have sent it to the hardware, but hardware has not yet processed it. And after it, hardware has processed it, it will go to the post-process state. And the corresponding driver functions are being given to move the descriptor from one state to another state. So the free descriptor are the one that can be allocated by the application using the AXI that can be allocated by the application before this one. So the BDs, when you create the BDs, they are in the free stage, and this free state BDs can be used by this function, BD ring allocate function, to allocate it to the particular DMA. Okay. So after allocation, they will go to the pre-process state. So the BD that have been allocated with this BD ring allocate function will be in the pre-process state. So these are in the application control. This application modifies this BDs to include the pointer to the next BD, then the buffer address, buffer length, and so on, and then prepare them for the DMA transaction. After that, the application send it to the DMA. So the BDs that have been send it to the hardware are using this function BD ring to hardware goes to the hardware state. These are in the hardware control, and maybe in this they are awaiting the hardware processing or in process. The application, once the BD is in the hardware state, the application cannot change the value of the BD or any content of the BD, otherwise the error will happen. Okay. So this may lead to the error or the even data correction. After the hardware process the BD, it goes into the post-process state. Okay. So the BDs that have been processed by the hardware and then have been extracted from the hardware using the AXI DMA BD ring from the hardware driver. So after you execute this function, BD ring from the hardware for the completed BD, they goes into the post-process one. These are now in the application control. These are now in the application control. The BDs can be checked. The application can check the status of these BDs by using the status register. Then by application can make this BD free for some other transaction by using the corresponding BD ring free function. Okay, so these are the states of the BDs are important. So you can see that the in the beginning, if you see in our previous slide, all the BDs were in the free state. Now we have created one BD. We have created the one BD in that. So here you can see that the we have created the one BD, but it is in the free count state. And now we need to what we need to do is that we need to convert this BD from the free count to the pre-count state. So for that we need to use the corresponding BD ring allocation function. Okay, by using the BD ring allocation function, we can send the BD to the pre-count state. Now, in the meantime, since we have created the BD, we need to initialize the BD with a certain known value. So for that, we have this we have this template which is defined as a 16 32-bit values. First two are the addresses, and the rest are the BD detail. So we will use this driver function to create the BD template. This BD template initialize all the values except the first two, which is pointer to the next BD with the 0, and we will use this clone function inside to copy this template in all the BDs. In our case, it is only one BD, so we will use this function to copy this template in all the BD. The BDs is still in the free state, so you can see that the BDs are at this location. The MM2S BDs are at this location, which is the address is given here. The address is this one, and this is, you can see that the first address are already updated. This is pointer to the next BD. Since there is only one BD, so it is pointer to the same BD. And if you see that this is the garbage value, after this one, this value should be initialized to 0. And you can see that the values are initialized to 0. Now we are in the BDs are in the free state. They have been initialized with the some values, not the desired value, but with some value. Now we can write the address of the current descriptor in the DMA register. So by using this XDMA BD ring start TX ring pointer, what we are going to do inside the DMA register, we are going to write in the current descriptor field, we are going to write the address of the first BD. In our case, it's the first BD only. So it will only one BD, so it will take care of that current descriptor. It will not write to the tail descriptor yet. It will just write to the current descriptor, and it will set the RS bit to 1 so that the DMA can start running. Now you can read the values of the corresponding register using the XCST control. So you can see that the current descriptor field inside that DMA has been initialized. Similarly, you can read the status of the control and the status register. So you can see that in the control register, the RS bit should be 1. So you will see that the value is now changed to that. Instead, in the previous case, it was last hex value was 2. Now it should have been changed to 3. You should verify that. Okay. So I was talking about the this bit. Now this bit is set to 1. This bit is 1. These are 0. So you can see that the value will be 2 instead of the 3. So these are the changes happen after you do the XDMA BD ring start. So we have done the setup for the MM2S. What we did, we disable the interrupt in the control register. We created the BD. We set the current descriptor pointer in the DMA register with that BD1, and we set the RS bit to 1. The same process we will be doing for the MM2S. Same process is that the code is same. Now the next part is that we need to now fill the BD with the appropriate information and then send the BD to the hardware state. Now in our BD, as we know that we are going to use only one BD in this process. So in the MM2S BD, we need to send the DMA input. We need to make sure that the DMA input address is there, and S to MM we have the DMA output address. Something like this we need to do. Then we need to send the BD to the DMA. DMA will perform the appropriate task, and how we will send, how we will trigger the DMA by writing the tell description address inside the DMA. In our case, since there is a one BD, so tell descriptor address will be same as the current descriptor address. Then wait for the DMA, and we can use the polling mode to see the completion of the DMA task, and then we do the comparison with our benchmark rate. So now in this one, in the previous case, we used the MM to S. Then we say that the S to MM is same as the MM to S. We did the state setup. Now I will discuss how to do the buffer descriptor setup for the S to MM. Okay, and then the same process can be used for the MM to S. So we have already created one BD for the S to MM. Okay, and this is at the location 0100 1000, and it is 16 32-bit values. Out of the first value is initialized with this one, first to 1, and the rest values are initialized to 0. So in our main code, we will receive the value, we receive this pointer in the get this copy of the pointer. Okay, and then what we are going to do is that we are using this function. We are going to have our own local buffer descriptor pointer. It is again an array of 16 32-bit values, and we are going to copy the address here. Okay, so this is the first two location of this pointer will be initialized with that address of the BD, that is 0x01 1000. Okay. So you can see that the at this one, you can see that this one is written, and this is my BD. Now what I want to do is that I want to update the remaining field. What are the remaining field? I want to update the buffer address. Buffer address, I'm giving some memory in the buffer, which I want to, where I want the DMA to write the data. So I'll write that address here. Okay. Then I want to set the buffer length field in the control register of the DMA. So this will be 8 into 8 into, this is the 32 bits, so it is 4. So it is 256. So in the hex, it will be 0x100. So here you can see that after this, this is the address in the okay. So you can see here, this is the address in the DDR memory where I'm going to receive the data. This is my control register inside the BD. This will be my status register, and the rest of the data you can see that the I have, in case of the S to MM, the start of frame and end of frame should be 0, which is again in the part of the control register. And this is the optional state of setting up the ID, but this is the optional steps. So in the BD pointer, these are the important things you need to take care. This is the pointer to the next BD, address, and the control register you need to set, and you can read it from the status register. These are the important things you need to take care. The same process you need to do it for the S to MM to S buffer descriptor. You can see that in the MM to S buffer descriptor, the process is same. Only thing is you need to make sure that the start of frame and end of frame bits are set to 1 in the control register. Rest of the process is same. After I have now created the buffer descriptor, now I'll send the buffer descriptor from the to the DMA, and I'll trigger the DMA by writing it to the tell descriptor field of the DMA. And for this, I'll use this function BD ring to hardware, and this function will write the tell descriptor address inside the DMA, and will start the DMA. Then I'll use the polling mode where I'll wait for the completion of the one buffer description. After that, I'll come out of the while loop. Then I'll compare the, this is the optional step where I can free up the BD so that this BD can be used multiple times for the subsequent operation. Then once I receive the data at that particular address, I'll compare that data with my benchmark software output, and along with the output, I'll also get the execution time, which is here. So here you can see that the HGDMA is slightly faster than the simple DMA, even though we are using only one buffer descriptor. When we use the multiple number of buffer descriptor, you will see that the HGDMA is significantly faster than the simple DMA. So in the next video, we will quickly discuss the demonstration of the SDK code along with the how we can debug it line by line. We will discuss it in the next video.